strategy dash equilibrium. Okay, so we just show that there are only two pure strategy dash equilibrium, AA and BB, but still it is still potentially possible that we have a Nash equilibrium such that either player 1 or player 2 randomizes. Okay, so that's our next question. Okay, so there are two cases. I mean, let's say there is a Nash equilibrium such that either player randomizes. Okay, let's say there is such a Nash equilibrium. Then there are two cases. Case 1, it is player 1 who randomizes. Case 2, it is player 2 who randomizes. Okay, so of course, two cases also covers the case that both players randomize, right? So anyway, so let's look at the first case first. Let's say player 1 randomizes A and B, okay? And let's see what such a Nash equilibrium will look like, okay? So here is our reasoning. I mean, I think I already did it last week, but let me repeat one more time. So suppose that there is a Nash equilibrium such that player 1 randomizes. Okay? Let's say there is such a Nash equilibrium. Okay, so then that means, okay, so player 1 randomizes, and that means player 1 has to be indifferent between choosing A and choosing B, right? Otherwise, player 1's randomization can never be a best response. Randomization can be a best response only if player 1 is just indifferent between A and B. Okay? So that means we have to have U1 a sigma 2 star. So I'm going to put star here to indicate that this is equilibrium strategy of player 2. So we don't know anything about this one yet, right? So for now, this can be any strategy. We have absolutely no idea about what sigma 2 star looks like. Okay? But anyway, we know that we don't know much about this, but we know for sure that we know this is true for sure if there is any Nash equilibrium such that player 1 randomizes. Okay? Okay, so and what's this? So this is player 1's expected payoff when this guy, player 1, chooses A while the other guy chooses plays the mixed strategy sigma 2 star. And this is equals to, okay, so there are two possibilities. With this probability, player 2 will choose A, right? So this is the probability that player 2 chooses A. And in that case, player 1's payoff is U1AA, right? So player 1 chooses A, and with this probability, player 2 will choose A. Plus sigma 2 star B. So this is the probability that player 2 chooses B, and with this probability, the outcome will be A and B. Okay? But we know this payoff is 0, right? If they choose different actions, payoff is 0, so this term then is gone. So this is 0. And what is it? This is 2. U1AA, that is equals to 2. So we have, so this payoff is equals to this probability times 2. And what about this? So there are two outcomes again, BA and BB, right? So but we know that the payoff, player 1's payoff from BA is 0. So this expected payoff is just equals to the outcome be A because we know that the payoff is 0. And this payoff is actually equal to 1. So we have this. So this payoff is equal to this. Okay? So we are looking at looking for a Nash equilibrium such that player 1 randomizes. So two payoffs has to be equal. Okay? If this payoff is strictly larger than the other one, player 1 has to choose A. He has to not randomize, right? If this is strictly larger than this, player 1 has only one best response, meaning player 1 has to choose A. Okay? And if this is larger than this one, then player 1 has to be choose B. Right? But that's both two possibilities are, but we are looking for Nash equilibrium such that player 1 randomizes. So we have to have two things becomes equal. Okay? Okay, then so this probability and this probability, that has to be, the sum of two probabilities has to be equal to 1, right? So which means that this has to be equal to 1/3, and this probability has to be equal to 2/3. Okay? Any question? Okay, so our conclusion so far is, okay, so we are looking for Nash equilibrium such that player 1 randomizes, but if there is any such Nash equilibrium, actually player 2 also has to randomize with that probability. Okay? And that randomization of player 1 is necessary to justify player 1's randomization. Okay? So that's our conclusion so far. Okay, and next thing we have to say here is, okay, so we are looking for this kind of Nash equilibrium, but if there is such Nash equilibrium, player 2 has to randomize. And if player 2 randomizes, then by exactly same logic, by switching the role of player 1 and player 2, we can show player 1 also has to randomize. With exactly the same probabilities. Okay? So player 2 randomizes. That means player 2 has to be also indifferent between A and B. Okay? And that will lead to this conclusion. Exactly same way here, but switching the role of player 1 and player 2. Okay? So in conclusion, if there is any Nash equilibrium such that player 1 randomizes, this is the only possible Nash equilibrium, like that. Player 1 and player 2, they randomize A and B with probability 1/3 for A and 2/3 for B. Okay? So that's the only possible Nash equilibrium that player 1 randomizes. And in that equilibrium, actually both players are randomizing. So there should be no other Nash equilibrium. Okay? So it is kind of straightforward to check this is indeed a Nash equilibrium. Okay? So actually, it's kind of redundant in some sense. We already showed that player 1 and player 2 are indifferent between A and B, right? So which means that both players have no profitable deviation in pure stretching. Okay? So we have three Nash equilibria, AA, BB, and one mixed strategy Nash equilibrium. And that's it. We have three Nash equilibria, and there is no other Nash equilibrium for this game. So this game has three Nash equilibria. Okay? Okay, so the next example is rock, scissors, and paper. But let me do this example first one. Okay, so let's do some more interesting, more interesting example. So this is probably one of more interesting example compared to the coordination game or prisoner's dilemma. Okay, so this is the game you can think of two firms, profit maximizing firms play together. Okay? So there are two firms, A and B, so the set of players, capital N is 1 and 2. So there are two firms, player 1 and player 2, or firm 1 and firm 2. And both of them have exactly the same actions. So in this case, we assume that both firms choose prices. Okay? So A1 equals to 5 means player 1 chooses price equal to 5. Okay? So I'm sorry. So actually, I'm going to use notation P. Pi is the price chosen by player I or firm I. Okay. So both players have to choose one price from the non-negative real numbers. Okay. Okay. Then the outcome is, and I'm sorry. So. Okay, so on demand side, there are two firms, exactly homogeneous firms, selling exactly the same product, 1 and 2, firm 1 and firm 2. And on the demand side, there are a huge number of consumers, okay? But let us describe the demand side with the demand function dp. Okay, so dp is demand, total demand when market price, when price is P. Okay? So demand function tells you that, let's say the market price is $10, then D of 10 is the total demand when the market price is 10, okay? Something like that. And more specifically, we're going to assume that demand function is linear, thus in this sense. So there are two parameters or numbers such that demand is given by alpha minus beta t, okay? And beta and alpha, both of them are positive, so it is decreasing in t. As you increase price, demand decreases. Okay, I want to actually use max 0 and this to define dp, just in case market demand, alpha minus beta p is negative. Okay, so in that case, instead of saying that demand is negative, it is more natural to say that demand is actually 0. So just for this case, I put max, on the slide, but it doesn't really matter now. Okay. So if you draw the demand function, demand curve on the diagram here, so we have total quantity here and price here, then demand curve looks like this. Okay? So when price is 0, total demand is alpha, and when price is alpha over beta, total demand is 0. Okay. Okay, so they choose. So two firms play the pricing game with this math function. Okay. So the rule of the game is basically if you charge strictly lower price than the other guy, then basically you win the entire market. Okay. which is kind of natural because remember that we have assumed that two firms are exactly identical. They offer exactly the same product. So if you are a consumer in this market, you will purchase from the firm offering lower price. Okay? And if you offer strictly higher price than the other guy, then your profit will be zero. Basically, your revenue is zero, so your profit is also zero. Okay? And if two firms charge exactly the same price, then we assume they share the market equally. Okay? So the firm's revenue, firm one's revenue will be P1 times 1/2 times D of P1. So exactly the half of the total demand, and the same thing, same revenue for firm B. So all these information are summarizes on the slide here. Okay, so here C is marginal cost. Okay, so here we assume both of them have the same marginal cost, and there is no fixed cost. Okay. Okay, so then what is Nash equilibrium here? So let's focus on Nash equilibrium in pure strategy. Okay? And then the first thing, okay, so we are looking for pure strategy Nash equilibrium. So fix any P2 for now. Okay? So P2 is supposed to be the candidate of equilibrium price charged by firm 2. Okay? For now, fix P2. Okay? Then for any P2, let's ask what is the best response of firm 1. Okay? Sorry, so now let's assume P2 is larger than C. Okay? So if P2 is smaller than C, then profit of firm 2 will be negative, right? So it's kind of silly to charge price less than C. Okay? Of course, it is still possible that charging exactly equal to C, but for now, let's focus on the case P2 is strictly larger than C. Okay, then what is the profit of firm 1? So this is P1, U1, P1, P2. So that's on the vertical axis, and on the horizontal axis we have P1. First of all, as long as P1 is strictly larger than P2, then what happens? If P1 is strictly larger than P2, then the revenue of firm 1 will be 0, because there will be no demand for player 1. So the payoff will be 0. Okay? What if P1 is exactly equal to P2? I'm sorry, let's look at the case that P1 is strictly less than P2 first. Okay? Here is C, and let's say P1 is between C and P2. Let me put it this way, sorry. So, we already, so this is right? This is correct. I mean, if P1 is larger than P2, payoff of player 1 will be 0. And if P1 is exactly equal to P2, then what happens? Basically, both firms share the market together, right? And as long as price is larger than P2, price is larger than C, profit will be positive, right? So we don't know exactly what it is, but we know that the profit will be positive. Okay, in that case, P1 is equal to P2, player 1's profit will be positive. player 1 offers slightly lower than P2. Then, first of all, if P1 is very close to P2, profit per unit will be also very close to P2 minus C, right? So there is no really loss in terms of profit per unit. So if P1 is just below P2, okay? However, if P1 is just below than P2, then player 1 basically can wins the entire market, okay? So if player 1 charges just below than P2, then profit will be jumps up something like this place, right? I mean, there should be some discontinuity here. When price is slightly less than P2, profit will be this high because player 1 can win the entire market share. But if player 1's price is exactly equal to P2, then this guy will half of the previous market share, so profit will jump down. Okay? And if P1 is way smaller than P2, then we don't know. I mean, there should be some graph like this. Okay, I just draw random graph, but I'm sorry. Actually, the graph looks like more pretty than this, something like this. Okay. So we don't know whether profit is increasing or decreasing here because there is both positive effect and negative effect when you increase price. When you increase price, of course, profit per unit will increase, but at the same time, given that demand function is decreasing in heat, the market, the quantity will decrease. So it is not clear whether this is increasing or decreasing over this range. Okay, but it's gonna be some kind of some graph here. We'll see some graph. I'm sorry. So more precisely, profit will be 0 here, right? When P1 is equal to P, exactly equal to C, profit will be 0. So graph, precisely speaking, graph looks like something like this. Okay, then this is the question. Now, here is the question. Okay, so do you think there can be any Nash equilibrium such that P2 is strictly larger than C? So we are looking at the case where P2 is strictly larger than C, right? In that case, we just draw the payoff function of player 1 as a function of P1. Okay? So what is important here is there is some discontinuity jump around P2. Okay? So my question is, based on this information, based on this observation, do you think if there is any Nash equilibrium such that P2 is strictly larger than C? So the answer is there is no such Nash equilibrium. So why? In Nash equilibrium, by definition, both players have to choose a best response against each other's, right? But in this case, actually there is no best response for player 1. Okay? So let's try. Let's ask whether this is Nash equilibrium. I'm sorry, whether this is best response or not. Clearly it is not best response because I think there is something wrong here. Okay, so now I can figure out. Okay, so Okay, so we are still asking the same question. If there is any Nash equilibrium such that P2 is greater than C. Okay, So the answer is there is no such equilibrium because if there is, suppose for now, just suppose for now, there is such Nash equilibrium. Okay? So then it is clear from this picture, player 1's best response is strictly less than P2. Okay? Actually, it has to be somewhere between C and P2. Because any price strictly larger than P2 is not good because profit will be 0. And price exactly equal to P2 is also not good because if this guy chooses, if player 1 decrease price a little bit, then profit will jump up. So again, to any price larger than C, player 1's best response has to be between C and P2. Okay? But then we can ask the same question for player 2. Okay? Then we can, by the same logic, we can conclude that player 2's best response is also between C and P2. I'm sorry, C and P1. Okay? So which means that the initial price P2 we fixed was not best response of player 2. Okay? So more intuitively, here, player, as long as the other guy charges strictly higher than C, I always has incentive to undercut the other player's price. Right? So as long as the other price is strictly larger than C, there is always such undercut, incentive for undercutting the other guy. So for that incentive for undercutting, we don't have Nash equilibrium such that any player's true choice is strictly larger than C. Okay? If P2 is larger than C, player 1 has to choose price strictly less than P2. Then after that, player 2 also has incentive to choose price strictly less than P1, right? And etc. So we cannot get into equilibrium, never. As long as P1 or P2 is strictly larger than C. Okay? Is it clear for everyone? Okay, so then at the same time, we can also exclude any possibility that either P1 or P2 is strictly less than C. Right? Because, okay, so we can, I'm sorry, let me be more precise. We can also exclude the case that both P1 and P2 is strictly less than C. Then what happens? Price is less than C, that means some players' profit is negative. Right? But that's clearly not a best response because a player always can charge very high price, making his or her revenue and profit equals to 0. So both players always has an option to make zero profit. So any equilibrium with negative profit cannot be a Nash equilibrium. Okay? So then the only remaining possibility is P1 is exactly equals to P2, which is exactly equals to C. Okay? So if there is any pure stretched Nash equilibrium, it has to be P1 equals to P2 equals to C. Okay? Okay, then the next question is whether P1 equals to P2 equals to C is indeed Nash equilibrium or not. That's actually kind of straightforward. Let's focus on player 1. Given that the other player 2 chooses C, there is no reason to charge, so let me slow down a little bit. When P1 is equal to P2 is equal to C, then profit for player 1 is 0, and player 2's profit is 0. Okay? So let's focus on player 1 for now. If player 1 deviates and chooses P1 strictly larger than P2, what happens? Then player 1's profit will be 0, right? P1 is larger than P2, so there is no consumer purchasing from firm 1, so profit of firm 1 will be 0. Okay? So deviation result in 0 profit, which is equal to the equilibrium profit, right? Which means that player 1 actually has no incentive to deviate and charge higher than C. Okay? And next, what happens if player 1 deviates and charge lower than C? In that case, player 1 can win the entire market, right? But price is lower than my marginal cost, so profit will be 0. Profit will be negative. So that is clearly not profitable deviation. So that shows that player 1 has no profitable deviation, and actually his or her best response is exactly equal to C when the other firms also chooses P2 equals to C. And exactly for the same reason, player 2 also has no profitable deviation. So indeed, P1 equals to P2 equals to C, that is a Nash equilibrium. Okay? So here, again, in this case, it suffices to check whether there is any profitable deviation in pure strategy. We don't really have to bother with mixed strategy, deviation in mixed strategies, thanks to our first lemma here. Okay? So we don't really have to check mixed strategy when we show player 1 and player 2, both of them have no profitable. Any questions so far? Okay, so this actually not really difficult to conclude, to say that this one is only the unique Nash equilibrium in pure strategy. So the next question we can ask is if there is any Nash equilibrium in mixed strategy. Okay, so that's separate question. But this question turns out surprisingly difficult to answer actually. Anyway, it's kind of a difficult question. Sufficiently more difficult than the question whether there is what is Nash equilibrium in pure strategy. So mixed strategy Nash equilibrium is difficult to find out here. The answer is actually yes, there is mixed strategy Nash equilibrium. You can construct a Nash equilibrium such that player 1 chooses C and player 2 randomizes. Okay? I don't really want to go into detail, but there is such Nash equilibrium. But I think that's too much for now. Okay? So it suffices to see that this one is only pure Nash equilibrium, and it's gonna be good to know that there is also mixed strategy Nash equilibrium. We don't really want to discuss that in detail for now. Okay? Okay, so let me move on to the next example. So this is another game between two players, kind of similar environment, but in previous game, two players choose prices, P1 and P2, right? But in this example, let's say two firms choose quantity, not price. Okay? So again, demand is given by linear demand function. So demand function is again linear. We have Q here, P here, so demand function is linear and increasing in P. And player 1 and player 2, or form 1 and form 2, they choose Q1 quantity chosen by form 1 and Q2 quantity chosen by form 2. They make these two decisions simultaneously. Okay? So if form 1 chooses Q1 and form 2 chooses Q2, then the total quantity, total supply will be Q1 and Q2. Okay? And then, and we assume that once they choose their quantities, they cannot really change it anymore. So this is just, they have to come into these two quantities once they choose. They cannot really change. They cannot increase or decrease their quantity later on. Okay? So then, the market supply curve will be vertical, right? So vertical market supply curve means that supply is actually fixed at this level, Q1 plus Q2. Okay? Player 1 and player 2, they choose quantity Q1, quantity Q2 together. So the total quantity is Q, and that will never change. So the market supply curve will be vertical, meaning that the supply quantity is fixed at this level. Okay? So then, probably you already have learned equal 101 that the equilibrium price will be here, where demand is equal to supply. Okay? So then once we have market price, then we can calculate profit of form 1 and profit of form 2. Okay? So then these profits level, these final profit levels will be the payoff for player 1 and payoff for player 2. Okay? So that's the rule of the game. Player 1 chooses Q1, player 2 chooses Q2 independently and simultaneously, and then the market price will be determined by demand function, right? Like in the diagram. And then player 1's profit is realized and profit for player 2 is realized and that's it. That's how this game is played. Okay, so there are two players. And again, let's look at player 1's best response and player 2's best response separately. So form 1 first. So form 1 would like to maximize its profit by choosing Q1. Okay? And so form 1 would like to maximize profit by choosing Q1. And what is profit? Profit is price minus Q1. Price minus C. So here again C is marginal cost. So this is price minus C, that is profit per unit times Q1. So that's the profit of form 1. Okay? So form 1 would like to maximize Q1. Maximize profit by choosing Q1. Okay? But we know that profit will be determined by our demand function, P. Okay? So actually price is function of Q1 and Q2. Okay? So this is total quantity. So I'm going to use capital Q to stand for Q1 plus Q2. So small qi is form i's quantity, while and capital Q is just sum of all quantity. Okay? So price is function of Q1 and Q2, actually Q1 plus Q2 minus C times Q1. Okay? Moreover, we know that in the problem, the example, actually this function is given by alpha minus beta times q. Okay? So we know actually this function p is actually equals to alpha minus beta times q1 plus q2 minus c times q1. Okay? So this is profit function of from 1 when player 2 chooses q2. Okay? So profit is price minus c times quantity, but we know that p is price is alpha minus beta times q1 plus q2. So we just replace capital P over there with alpha minus beta times q1 plus q2. Okay? So that's it. Okay, so this is the profit function when player 2 chooses Q2. Okay? But we know that actually player 2 can possibly randomize. Right? So, in this game, in normal form game, we always allow a player to randomize. If that randomization is, best response, of course. Okay? So this is profit function when Q2 is a just number without any randomization, right? But we also like to take into account the possibility that Q2 is Q2 is random variable because player 2 randomizes. Okay? So what we have to actually put as the objective function is actually not this one, but expected value of this profit. So this is profit when I choose Q1 and the other guy chooses Q2, right? But we know that this is random variable, possibly, right? Q2 is possibly random variable. So actually what player 1 would like to maximize is not this 1%, but expected value of this profit. Okay? Okay, so in conclusion, Form 1's problem is max Q1 has to be non-negative, of course, to maximize the expected profit. Alpha minus beta, Q1 plus Q2. So this is price when Q1 and Q2 are chosen, minus C, so that's marginal cost. So this one is profit per unit times Q1. Okay? So this is player 1's problem. Player 1 has to choose Q1 to maximize the expected profit on the board. Okay? Okay, actually we can simplify this a little bit more. So alpha is just one number, so this is not random variable, right? And beta is also not a random variable. And in player 1's perspective, Q1 is also not a random variable. So player 1 chooses Q1, so there is no really uncertainty about Q1 in player 1's perspective. But Q2 is random variable, right? Because player 2 can possibly randomize. And C is not a random variable. Q1 is not a random variable. So the only random variable is Q2 here. So this is actually equal to alpha minus, so this is the random variable beta Q1 plus expected value of Q2 minus C times Q1. Okay? I just take all non-random variables out of the expectation operator. Okay?